very much for coming to this session. So the first talk will be by Aziz Kharoof from University of Haifa on topological methods and contextuality.
Hi everyone. Thank you for the organizer to let me talk today. So if someone of you don't know topology, because I discussed with many people here and some of them said we don't know topology, okay, you don't have to know. Okay, I will explain everything. So what kind of contextuality I mean? So let's explain. So let's say that we have 3 experiments in quantum physics, and we doing them together, like experiment A, B, C. We're doing them together, and we have a result for everyone, 2 results, possible result, plus, minus, or 0, 1, like 0, 1 here. And we have this, like we can't measure for some reason. I don't know why. You maybe know, you physics. I'm a mathematician, by the way, so I don't know why, but let's say that every time we can measure only 2 of them. We can't measure the 3. We can't know the 3 results, what happened. We do the 3 experiments, but we can measure only 2. Like we decide, for example, to measure A and B this time, and we can measure A and B to know the result, or B and C, okay, like this. But the good thing that we can do this experiment, we can repeat this experiment as much as we want, okay? Can do this 1,000 times a day like this, okay, many times. So from this, actually, we can get a probability table, like we can decide to measure every time A and B, to do these many times and to measure A and B until it's like stabilized. So we have some probability table for the result of A and B. So we will get something like this. Like here, probability table for AB. So this number, for example, it's tell me what is the probability when I measure AB, when I decide to measure the result of A and B, to get 0 for A and 1 for B. Okay, this. Yeah. So of course the sum of this is 1. This is probability table for A and B. Same, we got probability table for BC, for AC. Okay. So what the properties, the mathematical properties of this probability table? So actually one can ask what is, for example, the probability to get 0 if we measure B. So we can get from this table, because we can go, okay, where it's B0, it's here and here, right? So we can sum both of this and we get the probability to get 0 by B. But we can go also here and say, okay, B to B0, I can sum this, both of this, right? So actually in this kind of experiment is the same. We will get the same results. Yeah. So we'll get that this equations. Okay. It's called non-signaling in this area for some reason. Okay, it's not important now. And now one can ask a question. Okay, we did the 3 experiments together, right? From the beginning, we did the 3 experiments together. So one can say, okay, maybe we can't measure the 3 together. We can measure just 2, but there is result for the 3. So if someone have some tool that to measure the 3 of them, so then he can get a table for ABC, right? Table like this. And he say, okay, this table induces these 3 tables. But the surprise is that not always we have something like this, okay? Not always. Like we can have some tables like this that have this property, but not coming from some global table like this, okay? As this, we call this such a table that not coming from such a global table, we call this non-classic or contextual tables. Okay, this kind of contextualities I am talking about, okay? Okay, so let now give his topological description. But again, if someone don't know topology, it's easy. You don't have to know, but we call this topological description. So what we can say, like for this scenario, what we started from the beginning, like we have 3 experiments and we can measure every 2 of them together. We can have another kind of scenario, like we have 10 experiments and we can measure this is 3 together and this 4 together and this like this. Yeah, so for this scenario, we can give this triangle to remind us A, B, and C, the points of this triangle are the experiment. And here, every edge tell me that I can measure these 2 together, right? And I can measure these 2 together and these 2 together, okay? And we have for every edge or for every 2, like probability, like what we probability table like this, right? Here's like a matrix. So it's the same what I wrote before. And what we say by equation, it's exactly to say that they coincide at B. Like if I'm going here and from by this, I want to know what is the probability of B to get 0, right? Then I can get it by this, as we explained before, and I got it by this, so this should be equal. So we have as a distribution here for B. Distribution for B, 2 numbers, like distribution n 0, 1. Here, distribution n 0, 1 cross 0, 1, right? 4, yeah. So we have this. It's the same we have here, but it will take a place, so I didn't write it here. So we have this. But another, some much modern description is using what's called simplicial sets. We don't have to know. Okay, let me tell you what is the other description using, let's say, using diagram, if you know, commutative diagram. Okay, let me explain this diagram that it's give me the same information as above. So here, actually, what we have is a map from this 3 edges to distribution. This D, I mean that all the distribution on Z2 cross Z2, like Z2 cross Z2 to give me the 4 results that we can have. All the distribution, because what we have here, actually distribution for sigma, distribution for tau, distribution for gamma. And also we have here for the point distribution, but distribution on Z2. And this compatible, like this diagram tell me that it's compatible. Like let's take example, like if I take sigma and I take D0, what I mean by D0? D0 is give me the end point of the edge, and D1 give me the first point of the edge, okay? So if I apply D0, so it's give me B for sigma. And then the probability in sigma will be this or this, okay? This is the same. But we can go like this, like we can apply P1 of sigma, which give me this probability table. And here applying actually D act not only on sets, it's act also on maps. So in the way I explain here, like this is the action. If I act on this by DD0, this will give me this. Okay, I don't have time to explain it's exactly what's happening, but it's okay. Like this, exactly this operations that give me this. And this exactly give me that this is the same. And if we apply applying this and this going to be by applying D1, it will give me the same result. So yeah, so we have this. And if one thing a little bit, like look at the left side here. Actually, the left side is description of the triangle by sets, right? That abstract description of the triangle, right? Like here we have all the point of the triangle, and here we have the edges, and this tell me what is the relation, which one is the end and the beginning of the edge, right? This give me. So this is what's called simplicial sets. This is the idea of simplicial sets. That we are actually given abstract description of some geometric shape. Like, okay, we say if someone knows simplicial complex, so it's some generalization of simplicial complex. But we can have more, like higher dimension. We can have triangles and then pyramids and so on. Okay, but this is only for a triangle which is like one-dimensional. Okay, so let's actually generalize this definition, which is non-definition simplicial sets. It's so useful in the area of homotopy theory, and infinity categories is so in mathematics is so useful, this definition. But this definition is tell me that I have a collection of sets that related together with space maps and degeneracy map. Forget about degeneracy map. We need it. We're not going to throw it because it's so important for the theory. Otherwise, it's not all. But we don't have time to explain, and it's not important for this talk, especially. So face maps, I mean exactly this, D0 and D1. So, and X0, here we have point, X1 we have edges, X2 we have triangles, and so on. So from X2, for example, to X1, we have 3 faces maps because every triangles have 3 edges, right? And so on, it's more and more faces. So this exactly generalize the left side, okay? And now I want to generalize the right side. So let me give this example of simplicial sets. This example of simplicial sets, because actually here we have as a point ZD, as the edge is ZT cross ZT. It's not describe something geometry directly, one can see. It's hidden, but it's okay. Like this also satisfies this definition. And what is the faces maps? The faces map is by deleting. Like I have here two ways to delete. I can delete this side or this side, right? The first number or the second. Here we have three options to delete, right? This or this or this, like this. So this we need for the this, and now we can give a generalization of these tables, what we have before. This I come back and tell you what I mean. I mean this table that satisfies this. We describe it by this way, and we now give some generalization for this, what it's called simplicial distribution. So simplicial distribution is a simplicial map. I will explain what simplicial map you already saw, but I will explain. So from some space, space I mean simplicial sets. We call this also space because it's in some sense is equivalent to topological space. Okay, so we have these X simplicial sets, and it's a map to. We apply the distribution as we did above to this delta, to this one. Delta of Z. D can be any number because I started with example with two outcomes, but it can be any number of outcomes. Okay, any finite number. Okay, so we call this is a measurement space X because it's tell me what it X like represent, like triangle there. It's tell me the what I can measure with what, right? What I can measure. And this D delta ZD is the outcome space because it's corresponding to the outcome, right? It's coming from the number D, how many outcome we have. By simplicial map, I mean like also as a simplicial set is a collection of sets, the simplicial map is a collection of map that makes the diagrams commutes here. Like here we have two because it's one dimensional, but we like a graph, but we can have more, okay? Yeah. Okay, let me continue. So we now have this definition of simplicial distribution, and now we will talk about the collection of all the simplicial distribution for fixed scenario, like we fixed X and fixed D, and we want to talk about the behavior of all the simplicial distributions, okay? So if we fix the measurement space X, so we will denote by this as all the simplicial distribution, like this from X to D of delta ZD. And this form a polytope. What I mean by a polytope, I mean something like this. Okay. So this is a polytope like some convex sets with finite number of vertices. Okay, so this is okay. Anyway, something like this you can think. There is a mistake, by the way, in this. I forgot to replace. I will tell you, but it's not important for the talk. But anyway, so all that is like every point here is a simplicial distribution in this shape. Of course, the shape is much larger. I can't draw this. Even for this simple example we started, it's much larger. Yeah, we can. It's hard to draw this, but this for explanation. And here inside we have the non-contextual simplicial distributions that coming from global table. And here is a contextual distribution outside. And here, a mistake that this should be vertex here, the green. This should be vertex, so this line don't have to be like this. Yeah, sorry about this, but it's not important for this. I want just to illustrate for you the that it's a polytope like this. And what people interested in this area for this polytope, then it's two important things. The following contextual vertices. Contextual vertex, I mean this one. It's in the contextual area, but it's vertex here, right? It's extreme point, it's extreme point, right? Here, there is. So it's not, in some scenarios, it's not easy task to find them, by the way. And the other thing is this line, the green line, which divide the area between contextual and non-contextual, between classic and non-classic, okay? This is important. So this is called Bill inequalities. Like it's okay, it's equation, but we can think about this inequality like that. Say when I am here, the conditions that I am here in the green, non-contextual, okay? So people are interested in this. And now we will show how this approach, the simplicial approach, topological approach, what we described a little bit before, how it's really useful for answering this question, like for some scenarios, okay? So now we will go to show this. So first method I will show is the collapsing method. Okay, it's hard for me, S and S. I don't have in my own language, sorry. So collapsing method. So the collapsing method, it's like this, we have like this, like think about this as a graph, simplicial sets actually, but okay, it's a graph. And let's say we collapse this edge and then we get this graph, okay? So we have a map like this from here to here, actually simplicial map, one can from here to here. Here, another example of collapsing. So here we collapse this edge to a point and we collapse this triangle to an edge. Okay, so we collapse like n simplex to n minus 1 simplex. We can repeat it. Okay, this is collapsing map and this is collapsing map. So when we have such a collapsing map, this map from the original space to the collapse space, like when we collapse from here to here, induce a map from the different direction between these polytopes, all the simplicial distribution here, all the simplicial distribution, all the tables, the possible table, all the possible tables here. Give me some maps. Actually, this map is in inclusions. This map is easy to describe. It's by composition. Like we have some simplicial distribution. We compose by this, we get simplicial distribution here. This map is injective and it's preserve convex combination. Okay. So, but we have more than this. We have the following result. For simplicial distribution here, we have the following, that this is contextual if and only if the image is contextual. Okay. And the other result, that this is a contextual vertex if and only if the image is contextual vertex. Okay. This is the result. So the first result, actually, it's the first one. It can be useful for Bell inequalities, but not too much. Like we can say, for example, that we have some new Bell inequalities here that people didn't know before, but it's coming from Bell inequality here. It's not like because people thought that like one of the weird Bell inequality, new Bell inequalities appears here for the first time, but it's actually appeared here, but it's not that useful. Actually, the second one is useful to find contextual vertices. So here is how we can use this. So if we have a directed graph, like simplicial sets is generalization of graph because it can have much dimension. But let's say we have directed graph. We can have a collapsing to a wedge of circles like this. Like we have this, what we had before. Actually, this is K33, by the way. This is K33. And we can collapse, like we can collapse this as we did before. And we can collapse another 4 edges. And we got this shape. And this shape is easy to describe the vertices here. It's not hard task. Here it's hard, but here it's easy to describe the vertices. But we know that by the theorem that every vertex, contextual vertex here will become contextual vertex here by this map pi star. It's me back. Like if we have pi like this collapsing, we have pi star on the opposite direction. And every contextual vertex here will become contextual vertex here. So by this, we can have the following result that if let's say like we have a graph with m point, and m is the number of the circles here, like here we have 4. Okay, it's given, by the way, it's have some invariant, the topological invariance related to some topological invariant. But anyway, let's think about this, that is the number of circles here. Then there at least this number of contextual vertices. D here is the number of the outcome. Okay. Actually, this together form a group, by the way, form a group. But this not by collapsing method. We can know this by other homotopical method, but we will not talk about this. Okay. So this always this is some general result for one-dimensional measurement scenario or directed graph when the measurement scenario is directed graph. Okay. Okay. Now we talked about contextual vertex. Let's talk about Bell inequalities. In this paper, actually, we talk about is there is a proof, topological proof for the Bell inequalities of such a scenario like this. What we called flower. This flower scenario. It's like we built by gluing by 2 points some lines. Here we have edges like this. We glue by this, and then we get something like this. A generalization of what called cycle scenario, and for other scenarios, generalization for some scenario. And there is a topological proof of the Bell inequalities of this. So this says that if we have simplicial distribution on this, but here actually it's hard to do this for, yeah, we did for the two, like d equal to do to when we have two outcomes. So something is non-contextual here if and only if the restriction on every circle here. We have many circles here, you see. We have many circles. If and only if the restriction of every circle is non-contextual. And non-contextuality on circle, it's like people know what is the Bell inequality. It's known Bell inequality for this. So this tell us that the Bell inequality for flower scenario also is the same as the Bell inequality for circle for every circle here. Okay, the same Bell inequalities. And in order actually to prove this, we use the following fundamental lemmas. Extension lemma. Extension lemma is tells us that if we have a measurement space and we can contain it in some larger one, such that everything here is a classic in this one, every distribution on this one is non-contextual. If we can find something like this, like for example, for the triangle, if we fill the triangle, we will get something like this, yeah. But then if we can extend some distribution on X to W, we know that this is non-contextual, okay, or classic. So we have this. The other thing, we have a gluing lemma. It's also an important lemma, useful lemma, that says that if we can, we can characterize X as a union of such smaller, it's 5 minutes, okay, for such smaller spaces, and they have intersection, but the intersection of them is n-simplex. What I mean by n-simplex, like point or edge or triangle or pyramid like this, yeah. If we gluing A and B through this and get X, then something on X is simplicial distribution on X is non-contextual if and only if it's non-contextual on A and non-contextual on B, like the restriction of this on A and B both are non-contextuals. Okay, so this actually is fundamental result, useful too much, especially for proving the previous theorem. Okay, I wanted to talk about another method. It's depend on vertices here, but let me back and say something. No, I don't have the time to talk about this, but let me say something that in this description, let me back here to the definition. In the definition, actually, we see that we replace the measurement space by, we see now as a topological space, but also the special of this language that we also replace the outcome between, instead of B numbers, it will be space also. And this space have some homotopical meaning. It's some kind of topology, some area in topology, and this can be useful. And it's already useful. It's already like there is like something that one can do by this. Okay. So finally, if you want to read the last things, it depends on it's about vertices. Some method about vertices we as a following result. If you're interested in, and that is thank you. What is the thank you? Oh, okay. Thank you for listening.
We have some question time.